Welcome all to the today's ECR presentation by Dr. Xiao. The topic of the presentation is forecasting and interpolation for learning physical simulations over meshes. Let me introduce a little bit about Dr. Luo. He is a postdoctoral researcher at UCLA Department of Computer Science. Previously, he received a BS degree in mathematics from Nanjing University, China in 2017, and a PhD in the School of Mathematical Sciences from Peking University, Beijing, before coming to UCLA and Computer Science Department. And his interests include machine learning on graphs, dynamical systems, statistical models, and AI for science. So very relevant topics in today's world, scientific world. So without much ado, let me welcome Dr. Liu. Dr. Liu.
Thank you for your introduction. Please let me know if you cannot hear me clearly, okay? Today, I'm going to talk a very important problem in modern scientific machine learning about how to use machine learning to learn physical simulation over meshes. First, let's talk about the background. Physical simulations are very important for understanding fundamental principles in various domains. Let's use some typical examples. For example, we can see a flag waving in the wind. So we definitely want to capture the movement of the flag. Also, we can use physical simulation to model a deforming plate. So you can see this is a metal plate with forces from actuators. A very famous physical simulation example is cylinder flow. It models the water flow around a cylinder in the river. So the model is driven by the famous Navier-Stokes equations. The last famous one is the airfoil model, which is very important in aerodynamics. It models the movement of air around the airfoil. There are two typical ways to model this physical simulation. One is to use regular grids. So if we use regular grids, these grids will divide the whole space evenly into a lot of squares. And then we can use like convolutional neural network to learn the dynamics. And the other one is to use irregular meshes. In this way, we can pay attention to more interested region with rapid velocity change, like this region near the airfoil. So based on our graph, our mesh-based graph, we can have our formal problem definition. So the dynamic system, as a dynamic system with both temporal and spatial correlation, can be represented using a mesh graph G with the node set V and the edge set E. And we are given the current state of mesh point xt0 to xt0 minus tau. And our objective is to predict the future trajectories for all the nodes from t0 plus 1 to t0 plus t. Then we want to first introduce some background of graph neural network. In graph neural network, we update node representation using the message passing mechanism. We can say, first, we can say for each node, we first aggregate the information from the node, from every node of its neighborhood, and then combine the aggregated information with the central node for updating. And here com and agg denotes the combination and the aggregation operators. For example, aggregation operators can be average or sum. And the combination operators can be recurrent neural network or use attention mechanism or some simple ones. Also, you can use average, right? So we will start like the graph neural network layer message passing layer for several for several layers, and then we can output our predictions. So in summary, graph neural network has been widely used in representing a variety of structured and complex data, including social networks, traffic networks, information system, knowledge graph, protein interaction neural network, and physical interaction networks. There is also a lot of model variant, such as graph kernel neural network, graph pooling methods, and graph transformer models. For 3D data, there are also equivalent graph neural network. So you can see graph neural network has been applied a lot. Then we introduce the most famous work in this line, MeshGraphNet, which is published in IDRE 2021. In this work, they use graph neural network to learn the spatial relationship in mesh-based physical simulation. Generally, they use the current time step to generate the differences of the state at the next time step. Then we can look into the detail. In the encoder, they have corollaries and the dynamic quantities. And then they use MLP. They use MLP to generate node embeddings and edge embeddings. Then in the processor, they update node embeddings using its surrounding edge embeddings. And similarly, they can update edge embeddings with current edge embedding and the node embedding at both ends. In the decoder, they use MLP to output the target. That's the differences of the velocities. So you can see it's a basically encoder, processor, decoder architecture. And they can feed the state at the next time step back to the input, and then use like an autoregressive method to generate long-term prediction. Then we introduce the second work, BSMS GNN. It's also our baseline, which is published in ICLR in SML 2023. This paper proposed a graph pooling method to improve the efficiency of physical simulation. Here they use UNet architecture, which involves several downsampling steps and which can reduce the node number in mesh-based graphs. After downsampling, they can conduct like the message passing neural network more efficiently. And they also have upsampling procedure, which can reconstruct the granularity of mesh-based graph. Because mesh-based simulation will involve a huge number of nodes, and in some regions, as we said before, the velocity doesn't change rapidly. So this method can definitely enhance the efficiency of physical simulation while keeping the performance of prediction. This work also put forward a new pooling method from graph determinations. We also have another important work called GMUS. It's also our baseline, published in ICLR 2022. This method selects pivotal nodes to compress the information into vector. In other words, we can get a vector to represent the compressed information at each time step. And then we can use transformer to learn the relationship across different time steps. Finally, we can reconstruct the state over the meshes using a graph neural network from the compressed vector. However, long-term forecasting is a very challenging problem in mesh-based physical simulation. We have introduced a lot of methods, but they usually use autoregressive strategy, which use the current state to predict the state at the next time step, and then feed the prediction back to the input in an iterative manner. However, we know that these one-step predictors could structure to capture long-term system dynamics, which could be governed by the underlying PDEs. Also, these methods are easy to accumulate errors overall, which could degrade the performance of their long-term predictions. So in our work, we propose a new perspective that learns from the future for present predictions. Our model takes a two-stage learning paradigm. In the first stage, we generate a coarse long-term prediction. We can call it foresight, like the yellow one. And in the second stage, we refine this coarse prediction into an accurate short-term prediction. You can see it as a blue one. Well, you can analogize it into by the comparison of the LSTM and bias LSTM. So in this way, we can learn from two directions. More importantly, we can learn from future dynamics. But how can we generate a coarse long-term prediction? Our solution is to use graph ODE. Here, we first introduce NeuralD, which equips neural network with a continuous dips architecture by parameterizing the derivative for hidden state. Graph ODE extends neural ODE to graph-based dynamic system. So you can see for graph ODE, FA and FR can learn the interaction between the central node and its neighborhood, which can decide the evolution of the states. We have mentioned our innovation is to use a new feature to present learning perspective to use a new feature to present learning perspective to effectively capture long-term predictions. So basically, our method first uses message passing neural network-based encoders to generate node representations, which are then fed into GraphOD twins to generate trajectories at different time steps. These predictions are then aggregated with the channel attention to refine the short-term predictions. So this foresight and the refinement steps are conducted alternatively for accurate long-term predictions. Then we move to our details. First, we need to introduce how we can get coarse foresight with the graph ODE twins. You can see it's basically an encoder ODE decoder architecture. The encoder and the decoder components are built upon message passing neural network, and our graph ODE twins adopt separate neural ODE to model the evolution of both nodes and edge. Here, xi is the input attribute of each nodes, and the pi minus pj denotes the distance between two nodes. Based on that, we can use the MLP to generate node representations and edge representations. During message passing, we update node representation with its associate edge representation and its current node representation. Also, we update edge representation using its current edge representation and its associated node representation. We also noted that data-driven prediction model often struggle to accurately deduce continuous evolution based on the current state. So we incorporate historical states as the supplementary data. Here we use them to augment the current embedding in ODEs. You can see we combine HIT and HIT T-1 as augmented embeddings, and then the evolution of node embeddings can be driven by the current node embeddings and its surrounding edge embeddings. Similarly, we also generate augmented edge embeddings. So the evolution of augmented edge embeddings can also be driven by the current embeddings and its associated node embeddings. Note that our graph ODE model can be considered as a special case of delayed differential equations, DDE for short, which has been shown being very effective to capture non-linear dynamics. We also show that our graph OD has a unique, absolutely continuous solution. Lastly, we use a decoder based on message passing neural network to provide the prediction at different time steps and minimize the mean square error for different time steps. So you can see our graph OD twins have two strengths compared with previous method. First, our approach is able to capturing the continuous interactive dynamics that naturally happens in mesh-based physical system. Moreover, our method is optimized under the framework of multitask learning. The reason is we generate prediction at different time steps, and each time step corresponds to a task. This task share the same encoder and decoder, but they have different prediction lengths. So this multitask learning strategy enable our model to learn long-term dependency with limited error accumulation. So definitely it can enhance the learning process. However, our graph OD also could underfit long-term trajectories in the multitask learning framework, like because it includes too many tasks, right? So here we want to introduce a refinement module, which use coarse long-term trajectories to improve the accuracy of short-term predictions. So here we use the prediction at time step T0 to TL, and then use the channel attention for aggregation. So here W0 and 2WL are learnable weight from the channel level. Then we can generate the offset of the prediction using the graph neural network, and then we can easily generate the accurate short-term predictions. So this refinement process can be considered as a form of interpolation. Compared with the one-step predictors, our models use the future prediction generated by the neural D twins for interpolation, which is empirically simple than extrapolation. Also, compared with the coarse foresight over multiple time steps, our refinement module targets a single time steps, which can enable us to further minimize the training loss. Finally, let's summarize our method. Our method has a two-stage optimization strategy. In the first stage, we train the model to generate coarse long-term predictions using a multitask learning framework. And in the second stage, we shift our focus to fine-tuning short-term predictions and remove additional separation You can see our algorithm here. We have the foresight step, optimization, and the optimization of refinement state. To generate short-term, long-term predictions, we can conduct foresight generation and interpolation, resulting pyramid-like architecture like this. During the propagation, our method can get insight from the future state, which can help in mitigating the potential error accumulation. Then we move to experiments. Here we introduce 4 basic datasets. We use 4 basic datasets to evaluate our model. The first one is cylinder flow, which simulates the never-stop flow of water around the cylinder on a fixed 2D mesh generated by the Cosmo. And Cosmo is a software. And the second one is an airfoil, which simulates the aerodynamics around the cross-section of an airfoil wing for compressible never-stop flow by CO2. CO2 is still a software. The third one is deforming plate, which is a hyperelastic plate in the structural mechanical system deformed by an actuator simulated by the Cosmo. The final one is inflating font, which can depict the inflation of font and characters. Then we show the compared performance of 7 competing approaches on 4 different datasets. You can see the dataset. From the result, we can see GraphUNet achieves the worst performance than other baselines. We know that the other baselines all target at dynamic system modeling, which shows the difficulties of mesh-based simulation. And therefore, we really need to design some physical approaches to solve the problem. Moreover, we can find our model performs the best across all the datasets in terms of short-term and long-term forecasting in most cases. For example, compare with the best baseline on each dataset, our method achieves an average error reduction of 25.1% in one-step simulation and 30.9% in all-step simulation. The performance improvement of our method comes from 2 different vectors. The first vector is we introduce our GraphOD twins in our first step, which can significantly reduce the error accumulation in our multitask learning framework. Moreover, we also introduced our refinement step, which can help us to use coarse feature prediction to refine short-term prediction with channel aggregation, and it can definitely mitigate the potential underfitting. Also, we can see that our method performed a little bit worse than MS GN grids in one case. The potential reason is the high complexity of the deforming plate, which could make it hard to generate accurate foresight, so it could degrade the performance. Then we show the validation of our method to compare with 2 baselines. And we can see this is the validation on airfoil. The first column is short-term, and the last column is long-term prediction. And this is the validation on cylinder flow. From the validation, we can find a serious error accumulation for one-step predictors. For example, in the last column, both MeshGraphNet and the BSMS-GN had a huge gap compared with the ground truth. And in comparison, our method can make accurate long-term prediction in most cases. The potential reason is our ODE-based model can capture continuous dynamics in physical simulation and also mitigate the error accumulation during the propagation. Besides, our model can also make accurate short-term prediction, which can show that our future foresight can also benefit short-term prediction as well. This picture shows the differences between our prediction and the ground truth. We can observe that our proposed method always have limited prediction errors, even for long-term prediction, which can validate our motivation and the effectiveness of our method. To evaluate different components in our method, we introduce 5 model variants. The first variant is called fair without ODE, which removes our graph ODE twins and only use one-step predictor for coarse foresight. The second variant called fair without R, which removes the refinement module and output the result using graph ODE. The second variant is fair without MTL, which removes our multitask learning framework and only involve the next time prediction in the refinement. The fourth variant is fair with E, which use the end-to-end method to optimize the whole model. The last variant is fair with cubic, which use a cubic interpolation instead of our refinement module. So we can have our compared performance in this table. First, our model definitely is better than fair without ODE, which can show that our ODE twins can really capture continuous dynamics and provide a high-quality future prediction. Second, our model also outperforms fair without R, which can validate our refinement steps is indispensable by preventing potential unfitting in multitask learning framework. And our model performs better than fair without MTL, so which can validate the future information is important to generate effective long-term match-based simulations. And our model also perform better than fair with E. So the potential reason is end-to-end training will involve all these modules simultaneously, which makes the training more difficult. And our model is also better than fair with cubic, which can validate the cubic interpolation cannot fully understand the complex relationship between different nodes during the refinement. Then we conduct sensitivity analysis of our method, which consists of 2 critical parameters. The first one is the step size, which is the size between 2 time steps during foresight. The second one is the future prediction number, which means how many time steps we are going to predict. So here we first change R in 1, 2, 3, 4, 5 with the other parameters fixed. So we can see first the error decrease and then increase as R increases. The reason is when R is quite small, a large R can provide a large horizon, while too large R could be far from our target, which makes our interpolation difficult. And then we change the future prediction number in 1, 2, 3, 4, 5, and we observe an error reduction when L increase before saturation, which indicates we definitely should include more future information to enhance the performance. Then we evaluate the prediction at different time steps. The left figure shows the prediction errors of different steps of different methods on airfoil. And the rest table shows the results on flex simple. So from the result, we can see our method had strong model ability with relatively lower errors at large time steps. But two baselines suffer from serious error accumulation. This can validate our method can make best of the foresight to reduce the error accumulation for long-term predictions. We also analyze the efficiency of our method and the two baselines. The left figure shows the computational time of one-step prediction on the single NVIDIA A100 GPU, and here 1, 2, 3 means the future prediction numbers, and definitely, if you have a large future prediction number, the time cost will also increase. And the right table shows the inference time, training time, and model size for different methods. From the result, you can see our method has similar efficiency with the compared method, but we achieved the performance increasement over 90.6%. This can validate the application value of our methods. And in other words, we can see a similar efficiency, but much higher performance for our method. Definitely, the time cost of our model will increase when L, the future prediction number, increases. So there would be a trade-off between the efficiency and the effectiveness. Therefore, we set L at 3 in our implementation and default. Finally, we compare our performance of 4 different methods on a noisy real-world weather dataset. This dataset records the radar reflective maps at different selected locations. The compared results are shown in the table in terms of MIC and MAE. From the result, we can see our method is definitely better than 3 compared methods. The reason is that our model follows a multitask learning procedure, which is definitely more robust to noisy data. So let's have let's summarize our work. We first introduced the problem of mesh-based physical simulation and related works, and then we proposed a new feature to present perspective to long-term dynamics. We also proposed a unified framework fair which adopts the graph of D twins for coarse forecasting and attention-based refinement. We also conduct extensive experiment to validate the effectiveness of our method. So in the future work, because now we use the model to study mesh-based physical simulation, so we definitely want to model more complicated scenarios such as rigid dynamics or other multi-agent dynamic systems. The second is the large language model or foundation model has achieved great progress in related areas, such as time series forecasting. So we definitely want to incorporate large language model to enhance the performance of physical simulation. For example, there is a paper published in NeurIPS 2023. This paper evaluates the performance of GPT model on zero-shot time series forecasting, and they only feed the historical number as a prompt, and ask the GPT model to output the future prediction. And from the result, we can find it achieves a very great performance. And so it's really surprising and impressive. So it's one type of large language model to solve dynamic related problems. And there is also a work published in this year's IDRE called Time LLM. This work introduced patch reprogramming to adapt time steps into large language model friendly input. Here they believe using prototypes can be more natural for large language model, and they use that to conduct alignment. So in this way, they can combine large language model and time series prediction. They also add a head to output the results. So so there are two types of two lines of the relative work. The first is zero-shot based. They directly use the large language model as a predictor, and the second kind of work is alignment based. So they do some processing to the time series or the input to make it more friendly to large language model. So we can see, so and also we have observed there are extensive graph large language model and graph prompt learning models. For example, Ji-Liang Tang's group proposed to use large language model to enhance the data from text-based graph, and they also study how to incorporate structure information in prompt. So because there are intensive works, so we definitely hope to incorporate them to study how we can use large language model to improve mesh-based physical simulation or other complicated scenarios. The preprint of our work can be found in this website. For more information, you can refer to the survey work. I also participated in this work. This survey work explores the recent advantages in how to use machine learning to improve computational fluid dynamics. And you can find the number of related work has been booming in recent 5 years from 2019 to this year. Well, there are so many papers in this area. And this work divides the forwarding method, modeling method into data-driven circuit, physical-driven circuit, and ML assistant numerical solutions. This work also introduced inverse design and control. And this work studied applications in 7 main domains, like aerodynamics, combustion, ocean science, biology, fluid, plasma, symbolic regression, reduced order modeling. So you can see, you can also find related applications if related to your field. So thank you for your listening. That's it.
Thank you, Dr. Lu. Any questions from the audience? Just unmute yourself because we are very limited number of people, like 8 people. So just unmute yourself and come online to ask any question. Okay, David's question is, if you have trained a model M on mesh A, can you directly apply the model to mesh B accurately?
It's a very interesting problem. Yeah, usually we call it like a zero-shot performance of like this learning-based method. Yeah, but now definitely if we directly train the model in one dataset and apply it in another dataset or another different mesh-based system, the performance will drop. Definitely, because it's also involved a small scale data. But if you use a large language model or some foundation model, if you include a lot of data sets, maybe it can enhance the generalization ability of the data-driven method. There is a work published in this year. They involve a lot of PD-based data sets, maybe maybe over 20 data set. In that case, we can adopt this we can adopt this per-trend method to a new dataset without any fine-tuning, or we can directly use the ability of large language model to generate what we want. Yeah, so it's a very interesting problem. Yeah, it's also our target in our future work to enhance the generalization ability of the mesh-based simulation. Thank you for your question.
Anybody else? So I have a question about this large language model. Oh, okay. David has asked, is it at all possible to embed physical governing equations as part of the loss?
You mean like the physical informed neural network? Yeah. Here is a data-driven method. If yeah, I totally understand. Yeah, they are. Yeah, maybe in the future work we will try that. But now, recent works usually use like the data-driven follows the data-driven line, so they don't they don't embed the physical governing equations in the work. And we also have a work published in this year's IDRE SML. It's called PGOD. In that work, we incorporate the coefficient of PDEs, yeah, in our model, and yeah, and that can enhance the generalization ability of our model. Yeah, maybe you can refer that. It's published in this year's IDRE PGOD. Yeah, but if you want to incorporate incorporate the PD, all the PD equations, or all diverse PD equations, yeah, there is no approach yet, but maybe we will incorporate it in the future work, because it can definitely provide a lot of knowledge, right, for especially for large model to yeah, to think about, right. Thank you for your question.
Anyone else? If not, let's thank Dr. Luo for the impressive talks and really great work. And you get back around 15 minutes of your time. Hope you have a great long weekend. Thank you.
Thank you.
Thank you, Xiao.
Thank you, TV. Thank you.